morning, colleagues. First of all, I'd like to thank CSET for inviting me. It's appropriate that I'm here today to share my research with you, considering that I left UNISA at the end of 2014 to be able to do it justice. I feel I need to warn you that you're going to see lots of graphics. My one PhD supervisor used to say, "Karen, explain these to me in words." And the other used to say, "Thank heavens for the pictures." Now, I realized for the first time when I was preparing for this occasion that the research impetus that has taken me all the way to my postdoctoral work actually started decades ago. I'm the oldest child of an electrical engineer and an automotive industry chemist. Now, my form of rebellion at 18 was to enroll for a humanities degree at UCT despite my sciences high school trajectory. And my first real job was in film production. But I was in the right place at the right time. My very first year of work saw the shift from celluloid to digital, and I was fascinated. I saw the resistance to the new technologies. I saw production processes, for which I was responsible, change virtually overnight. It meant totally different kinds of equipment, different jobs, different office and location requirements. People were thrown. I had editors who struggled to make the shift because suddenly putting that movie together literally required an entirely different set of skills, tools, practices, and attitudes. 1989, for me, planted the seed for what was to become kind of an overarching research question. What are the implications of increasingly technological forms of work and education? I'm going to start by giving you the contextual and theoretical frameworks that shaped my PhD studies on engineering problem solving in industrial sites. I'm going to introduce you to a key analytical tool, the research methodology, and then briefly summarize the main findings. I'm then going to step briefly into a different collaborative research project which looked at curriculum structures. And this will take us into the heart of the matter, epistemic access and epistemic transitions, and what this means for technology-based education. As you can see from this diagram, the research focus is multidisciplinary engineering graduate problem solving in the field of professional engineering practice. Now, this is in the context of the multidisciplinary knowledge base drawn on by these graduates as a result of their experience of the curriculum and pedagogy in the field of higher education. Now, the reason for this focus was widespread poor student performance in engineering qualifications. We all know the statistics: high dropout rates, low graduation rates, and we've all heard the employer complaints. Our graduates do not know how to apply theory, or they're not hands-on. The most recent employer survey sees 34% of over 40,000 employers surveyed across 42 countries, citing the lack of required technical skills as the key reason for being unable to appoint graduates. Now, based on my access to students and industry when I was teaching at first and third year level on a mechatronics diploma program, I believed that there was more to the so-called science engineering disjuncture. The hypothesis was that there are invisible knowledge code clashes and shifts in complex engineering problem solving dependent on technologies in the 21st century, and that these are unanticipated by our current curricula and pedagogy. What I set out to do was to understand what forms of knowledge, what kinds of code shifting real practitioners in industry engage in, so that we can improve what it is we do in education. And the final goal was to understand, from a knowledge perspective, what happens when we technologize curricula. Theoretically, the research is located in the sociology of education, specifically in what Bernstein calls the field of recontextualization, the space in which we take knowledge as it has emerged in the field of production and reshape it into our curricula and teaching. Now, I've argued that this too is exactly what the practitioner does in the field of practice. I use a number of analytical tools derived from Bernstein's concept of knowledge structures and the various legitimation code theory dimensions. When I first started working as the Communications and Engineering Professional Studies lecturer on the Mechatronics diploma program, we used to moderate collaboratively during dedicated staff sessions every semester, and we observed a strange pattern. There was a direct correlation between students getting distinctions for programming and my subject communications, but scraping through or failing the mathematics and mechanical subjects, and vice versa. Secondly, the classic bottleneck happens in the design subjects, where they're expected to put everything together. Now, essentially, a mechatronics curriculum consists of subject areas that could be classified as structures, power, and control. Now, imagine my delight when I discovered, as part of my simultaneous Masters in Higher Education Studies at UCT, Bernstein's concept of structure, power, and control. I had only ever thought of these concepts in the context of the conceptual design module I taught as part of the diploma. But I realized that Bernstein provided a very useful way of possibly understanding why it was that students brilliant in one subject area really struggled in another. So, very briefly, let's just talk about Bernstein's knowledge structures. Bernstein classified formal educational knowledge based on how it develops in the field of production. Physics is what we call a hierarchical knowledge structure. We have specific concepts strongly sequenced that absorb lower concepts. Mathematics is a strong horizontal knowledge structure. In other words, there are different mathematical languages, each with its own strong concepts or rules that are not necessarily applicable to another. The third type of structure, represented here by the discipline of logic, is a weak horizontal knowledge structure. Now, these are kinds of knowledge that borrow concepts and rules across families of the same type. They're constantly changing. Things become redundant, as in art or sociology. Now, acquiring these three different forms of knowledge requires entirely different kinds of teaching and learning processes. Now, using this classification system, I conducted an analysis of a composite typical mechatronics curriculum. And I wanted to understand how students worked with and integrated these different forms of knowledge in that dreadful bottleneck design subject. So for my master's, I mapped how a group of successful students spoke and wrote about the design and manufacturing stages of a mechatronic system over time. Now, this was done with a different analytical tool from legitimation code theory called semantics. This is about the relationship between conceptual and contextual meaning making and complexity and simplicity of meanings embedded in terms. Now, but I'm not going to elaborate further on that. Suffice it to say that the height on this graph is moments where they talk about disciplinary elements in more principled or abstract terms. The values closer to 1 are references to actual physical objects and processes. And below the line is where they draw on knowledge in the world, social or generic. Now, the key finding in that study was that integrating and applying knowledge is the ability to draw on knowledge from different disciplinary and regional areas and build the knowledge cumulatively by moving up and down a context dependency scale of what is known as semantic gravity. Now, the separable, contextually visible disciplinary regions are mechanical, so first the structure, electrical, power, and programming, control. And they generally flow in this order until they merge into a system. However, after this study, there were numerous unanswered questions. I had already observed that different sectors in which our students were employed foregrounded different forms of disciplinary knowledge. Different practitioners have different ways of working. And the key question was, how can the same qualification hope to prepare students for multiple complex contexts? Because this is essentially a technology-driven field, and these technologies are proliferating and developing at a rapid rate. And I knew I had to turn to industry itself if I wanted to understand how engineering practitioners navigate between different forms of disciplinary knowledge when addressing engineering problems in different industrial contexts. I wanted to look at micro problem-solving moments and what this might mean for our different qualification levels. I also needed a different analytical tool, something that accounted for how people work with different disciplinary phenomena. I selected the LCT dimension called specialization, and specifically the concept of epistemic relations. This is about the what and how of knowledge. The vertical axis is about the phenomenon in question, how strongly it is bounded by recognizable and legitimate principles, the strength of its internal identity. For example, a phenomenon such as gravity is more strongly bounded than something like love. The horizontal axis is about ways of approaching the phenomenon. The stronger the rules, the stronger the so-called discursive relations. There are far more fixed ways to approach and represent concepts like Ohm's law, for example, in contrast to the multiple ways we could approach something like philosophy. Now, the epistemic plane gives us 4 codes, 4 ways of thinking. The top right is called the purist insight. This is about recognized principles and associated procedures, such as the example of Ohm's law that I mentioned. The bottom right is recognized methodologies. Doesn't matter what the phenomenon is, this is like following a formula, the structure of an experiment, applying lean manufacturing rules, mathematics, economics. The model or the procedure of working with that form of knowledge is more important than what it is being applied to. The top left quadrant is called situational insight. There are many possibilities for addressing the same phenomenon. Choosing a new cell phone, for example. What I wanted to do is fixed, but how I do it is variable. In other words, which type of cell phone I choose, what can I afford, what functionality I require. The lower left quadrant is where there isn't a strongly bounded phenomenon or any fixed way to do things. And this could either be because we are now focused not on knowledge, but on knowers, the people in the system, where other things count, or because there is no legitimate or recognizable practice. Now, each of Bernstein's knowledge structures and each epistemic insight represents a kind of code, a way of thinking, and each code or insight is significantly different. Now, how did I use this? Very briefly, I had 50 volunteers working as mechatronics technicians or technologists in 3 different types of automation environments. They completed a questionnaire describing context, the most recent problem faced, and a technical description of how they solved the problem. I then selected 18 of 27 responses and conducted what I called a reenactment interview. This meant they took me through the problem with the actual artifacts. I used the epistemic plane to map their approach to and analysis of the problem and the subsequent synthesis of a solution. In other words, I tried to surface the disciplinary basis of their problem-solving process. Now, here are a few examples of what those problem-solving maps look like. Now, just to give you one, the top left example is case study B4. This is a practitioner working in research and development who encountered a problem getting a controller area network bus to communicate properly with servo motors that regulate a 3-axis robot. Now, the problem itself was essentially the failure of vendor documentation to adequately present the appropriate instructions to comply with the ostensible functions of the subsystem. Now, this problematic documentation emerged across the majority of case studies. Now, you can see this practitioner approaches the problem from a situational insight perspective, then moves into what exactly the doctrinal processes of the system should be, discovers the misleading information in the user documentation, and he then has to move into the purist quadrant to deduce the fundamental principles and appropriate procedures. Now, the thicker arcs in this case represent richer epistemic or disciplinary detail that he used when he talked about the physics, mathematics, and logic that he drew on in addressing this problem. Note this clear diametric code shifting. Now, I'm going to jump straight to a few findings. Problem-solving patterns emerge in relation to the different components of the problem-solving system, which can also be represented by the epistemic plane. Now, first of all, in terms of the structure of the problem, the elements of the system are both subservient to and guide the visible and invisible structural logic dictated by the laws of physics and supported by the relevant mathematics to determine optimal relations in a particular context. Now, as far as the problem-solving processes are concerned, each contextual category revealed a different problem-solving pattern. Now, a potential archetypal pattern is a clockwise cycle starting and ending in the doctrinal quadrant. In other words, starting with a fixed approach with some kind of method, moving into all the elements in that environment, including all the people and stakeholders involved, what the situation specifically entails, then into the heart of the problem in the purist quadrant, and effecting change that can be applied systematically from our doctrinal quadrant. Now, the most problematic code shift for practitioners is indeed from fixed to multiple approaches. We saw this on the examples I previously showed you with the use of no entry signs. Now, finally, the scale of the environment tends to dictate a preferred insight. Now, this is better represented graphically. Here we can see that micro to small environments tend to see practitioners working in the situational and purist quadrants. In other words, never losing sight of the phenomenon in question. Now, our modular systems categories, such as machine and panel builders or systems integrators, see this common diametrical movement between all the possibilities of the situation and the doctrinal rules of a particular possibility. In our large-scale environments, however, we see a predominant focus on people in the system and doctrinal procedures. Now, this is our problem. We tend to teach on the right-hand side of the plane, and our students and graduates' greatest challenge is the movement towards the left, towards multiple possibilities, towards weaker or more weakly defined phenomena, or where the phenomenon isn't clear. Now, from a curriculum perspective, there are 3 recommendations for this research. We need to recognize that the different disciplines imply different ways of thinking. We need to enable explicit code shifting between the different ways of approaching different phenomena. And thirdly, since we cannot teach for all possible contexts, I suggest we need to enable our students to develop a more conceptual grasp of the reality and principles of different professional contexts. I'm going to digress for a moment. Can any of you remember the CHE proposal to standardize the extended program system? In other words, the official subsidized addition of a year to each qualification type? Well, the proposal included 4 key principles. Foundation provision, that at the entry level there is a recognition that serious knowledge gaps need to be filled given problematic curricular assumptions about students' prior knowledge. Now, I suggest this is about recognizing the different disciplinary codes. The second principle was about epistemic transitions, the need to scaffold students' epistemic development beyond foundation provision. Now, this is about code shifting. The third principle was enhancement. There's a need for a structure that enables greater breadth of exposure in order to produce graduates for the contemporary world. Now, this breadth is about contextual codes. And finally, the question of enrichment. There is a necessity for curriculum enrichment through key literacies. I suggest this is about enabling the understanding of code principles, how different kinds of meaning-making codes work. Now, in a follow-up research project, a collaboration between 4 institutions, we looked at how these 4 principles were built into existing mainstream and extended curricular programs. And I'd like to draw your attention to 3 key curriculum structural differences. Now, we see foundation provision, the little staircase, across the STEM qualification range. But for the BSc, the enhancement and literacies enrichment are added on or external. In other words, they're not embedded in specific majors streams as they are in the BCom, or in specific subjects as they are in engineering. Now, the most important finding of this project, though, is the question of epistemic transitions. The BSc does not face a particular profession, so there isn't a transition into the applied or professional space built into the qualification structure. Now, the BCom may see a professional transition built into the final year of the majors, such as a research project on taxation or accounting practices in specific professional sites. Engineering, on the other hand, has a more complex epistemic journey through the qualification. And I quote, "The professional journey requires fundamental epistemic transitions, for example, in engineering from one kind of know that and know how of the basic sciences to another of the applied sciences to yet another of the design disciplines." Now, this is with reference to the bachelor's. We can add a 4th stage for application in practice in the case of the diploma qualifications. Now, this epistemic transition or epistemic journey is about the ability to code shift. Let's just return to Wally Morrow again regarding our mandate in higher education. Any established and disciplined practice can be said to be constituted by a particular, but not necessarily exclusive, grammar. Higher knowledge of the practice in question would consist in understanding the constitutive grammar of the practice, the grammar that makes the practice what it is. Now, what this means is that our job is to enable students to link abstract concepts to concrete contexts as we move from theory to practice within and across the curriculum. Now, this is what Mayton calls cumulative learning. What we've seen from the research I presented is that the different disciplines could be said to have specific codes, what I've called disciplinary home bases. However, access to each of these codes can be enabled by employing a different perspective. When we do experimental work in the natural sciences, we can do so from the situational quadrant, drawing on what it is that our students bring with them into the higher education space. Mathematics should not be stuck in the doctrinal quadrant. In my case studies, it emerged everywhere, in every single quadrant, and this points to Gauss's statement that mathematics should be about notions and not notations. What this means is that we should see our curricular and pedagogic work as enabling this complex shifting between insights over time, not necessarily in a neat linear way as suggested by the sine wave graphic. So what are the implications for ODL or blended learning or for technologizing our curricula? From a methodological perspective, I'd like to suggest that these are really useful tools to both interrogate and redesign our curriculum and pedagogy. Secondly, our one key challenge is that in order to enable code shifting along the how axis from fixed to open or multiple methods, we really need to take a look at our current assessment practices. It's far easier to assess on the right-hand side. It becomes far more challenging to open up those methods and approaches when you are assessing on the left-hand side. And thirdly, technology-based learning is located on the left-hand side of the epistemic plane. We see this in our students' difficulties with navigating a particular platform, in their fear of engaging in an online forum, for example. I'm going to share with you 2 examples of the use of these tools in redesigning curriculum and pedagogy in a blended learning environment. Here we have an example of redesigning a process control curriculum using the semantic wave to link theory and practice, and using the epistemic plane to design the intended code shifting activities for students. A research colleague of mine, Dr. Lydia Orette from Stellenbosch, used legitimation code theory semantics to differentiate between different levels of abstraction in her curriculum. She then used the traditional end-of-semester software simulation project as an anchor across the course to enable students to focus on different aspects of the practical project in relation to the specific theoretical elements at different stages. Now, when mapped onto the epistemic plane, what we see is that she explicitly enabled the students to code shift from the conservation of mass and energy principles to the equations to the use of software, bearing in mind the context of their specific projects and the moment in time that they were focusing on in that project. In a different example, we see the effective use of an online unit conversion and estimation competency test. Now, these lecturers teach chemistry to around 1,000 engineering students, and they had observed their colleagues' constant complaints about students not being able to estimate or convert units. Now, they set up an online randomized question bank, and students take the test repeatedly until they achieve 80%. And the questions are designed in such a way as to allow them to reinforce what the units represent, what the actual conversion procedures are, and to use multiple ways to approach estimation. Now, in closing, the epistemic plane could be used in ODL to allocate kinds of technology-supported teaching, learning, and assessment. Here are a few examples that I hope we can open for discussion. Finally, Laurillard urges us, as early as 2007, to interrogate technology-supported student learning, which takes us beyond the typical endorsement of a technology resource and enables a more refined understanding of the educational problem being addressed. In engineering, we know we need to enable epistemic access and facilitate key epistemic transitions so that our graduates can become the problem-solving practitioners our country so desperately needs. We must ask ourselves, what kinds of technologies, for what kinds of purposes, for whom and how? If we hope to achieve convergence to quality, then we need to recognize the different principles, procedures, possibilities, and people in our problem-solving equation. And I would like to suggest that this recognition is the first step in our collective decolonization project. Thank you very much.